Hi everyone, in today's video we are going to review simplifying square roots, and then we're also going to learn how to simplify cube roots today. So in this video we're going to review the exponent rules from Unit 4 and use those to simplify expressions involving rational numbers. We are going to review converting between radical and rational exponential notation formats. Then we're also going to be performing operations with radicals like adding, subtracting, multiplying, and dividing. And then we are going to go over rationalizing denominators. When we do square roots, that will be a review, and then cube roots will be the new concept. Okay, so first let's review the properties of rational exponents. So remember a couple of units ago, we talked about how if you have two bases that are the same, the two exponents can be added together and we can combine. If you have a base raised to an exponent and then that quantity is raised to another power, the power rule, then you can multiply together those two exponents. If there are more than one base and they are being held together with multiplication, then we can use the distributive property to distribute whatever that power is to each of the terms in the quantity. Now remember, this is not the same thing as addition and subtraction. This rule does not work. If I have x plus 1 quantity squared, that is x plus 1 times x plus 1. We can't distribute that power of 2 because this is not multiplication. This is addition here. The same thing is also true for subtraction. If I have x minus 3 quantity squared, then I have to write that as x minus 3 times x minus 3. I cannot distribute when it's addition and subtraction. It has to be multiplication there. Okay, so then we also looked at a negative exponent rule. If you have a base with a negative exponent, then that base with that exponent flips to the other side of the fraction bar. So in 4a, it comes down to the denominator. If the negative exponent is down in the denominator, then it can come up to the numerator to get rid of the negative as well. Similar to rule number 3, rule number 5 says that if you have a quantity that's being divided that's raised to a power, we can distribute there as well. It's only multiplication and division. It is not addition and subtraction. And then the last rule is if you have a fraction where both numerator and denominator have the same base, then their exponents can be subtracted. Okay, so let's get into some actual examples and practice. We also need to quickly review converting between notation formats, so let's think about that vocabulary again for a moment. Remember, when you have a radicand, that power that goes with it is the numerator of the exponent, and the index, or the type of root that you're taking, that is the denominator of the power. Remember, we talked a lot about power over root as a way to remember which number goes in which place when you convert back and forth between these two formats. So in numbers 1 through 3, we have radical expressions, and we are going to write them as rational exponents, meaning fractional exponents. So looking at this first one, this is a square root, and there's no power written inside with the 3, so we can assume that's a 1. Remember, our base is going to be whatever that radicand is. The power for that base is going to be our numerator, and the index is going to be our denominator there. So the square root of 3 is equivalent to 3 raised to the 1/2. For this next one, we have a cube root, and the 2, that radicand, has a power of 1. So that's 2 to the 1 over 3, power over the type of root that you're taking. All right, this last one, x is our base. The power is a 2, so it goes up top, power over, and then root, that's a 5th root. So power over root means we have x raised to the 2/5. We can also go back the other way, which is going to help us simplify radicals. So in this first one, we have 2 raised to the 1/4. So I'm going to write my radical. I'm going to put my base inside. The top number is the power, so that is a 1. And the denominator is 4, so that means the root that I'm taking is a 4th root. In this next one, my radicand is going to be x to the third power because the numerator is 3, and then the type of root that I'm taking is a fifth root. All right, let's do one more. Draw my radical, my 27 with my power of 2, and that is the 2 over 3, which means this is a cube root. Okay, so that was just a quick review of things that we've done earlier this year. Let's do a little bit of actual review of simplifying now. So we are first going to take our example 36 to the 3/2 and write it as a radical because we can't simplify it. There's none of those properties that we had in the first part of the notes are going to help us yet because we don't have another term. Okay, so my radical is going to have a 36 on the inside. The power is a 3, and the type of root that I'm taking is a square root. Now, if you'll remember, there was also this rule that we explored in the previous chapter, where if we see a root, like a square root, with a radicand that's easy to take the square root of in this case, then there's also a rule that says that we can write that radical, the square root of 36, and we can move this power of this single term to the outside. Now the reason I'm going to do that in this one is because the square root of 36 is easy to take. It's just 6. And then I can apply that power of 3. And 6 to the third power is 216. And that gets me to my simplified answer. Because this one had a nice square root with the radicand, I moved that power out and simplified the radical first. We're going to do some today that we will do that, and then some others that we won't do that as well, because they won't be quite as easy as that one. Okay, so let's do some simplifying of square roots and then also get into cube roots a little. So you'll recall that when we were simplifying square roots, we talked a lot about writing out all of the factors. So I'm going to do 1 times 48 for this one, and then 2 times 24, and then 48 divided by 3 is 16. And I'm going to stop right there because in my right hand column I have a perfect square root, and it's a big one. So I'm going to rewrite square root of 48 as the square root of 16 times 3 because the square root of 16 is 4. And then the square root of 3 stays inside, so that's my final answer. Now we can do the same process when we're looking at other types of roots. When we're looking at square roots, we're looking for a pair of numbers. So in this one, a pair of 4s. 4 times 4 came out of the radical. Another way of thinking about that piece there is if you're doing the square root of 16, that's the square root of 4 times 4. And because this is a square root, we're looking for that pair, so they come outside of the radical, and that's how we get just that 4. So when we're looking at a cube root, we're looking for a triplet. So a number 8, because the index is the 3, we're going to be looking for triplets or perfect cubes. Now on that perfect numbers sheet that you got earlier this year, there were some perfect cubes that I asked you to memorize, and this is going to be very, very helpful to you. If you do not have this set of numbers memorized yet, you need to do that today. So the list of perfect numbers that you're going to need is 2 to the third is 8, 3 to the third is 27, 4 to the third is 64, 5 to the third is 125, 6 to the third is 216, and 7 to the third is 343. This list of numbers is non-negotiable here. Get those memorized as soon as you can. We're going to do the same thing that we did for square roots with our new cube root. So I'm going to write 48, and I'm going to start listing out factors, but this time I am looking for one of these perfect cubes because this is a cube root, not a square root. In number 7, I was looking for a number I could take the square root of, but now I'm looking for a number that I can take the cube root of. Okay, so we know the beginning, 1 times 48, 2 times 24, 3 times 16, but that's not super helpful yet. So let's keep going. We have 4 times 12. No perfect numbers yet. 5 doesn't go into 48, but 48 divided by 6 is 8. And that does give me a perfect number. It gives me 2 to the third. So I'm going to write this as the cube root of 8 times 6. And then the cube root of 8, because 8 is 2 to the third, that gives me a triplet of 2's. So that 2 comes outside and the 6 stays inside. And don't forget about writing your radical there. So that's my answer for that one. Let's do a couple more of these. If I have the cube root of 64, remember I'm looking at my cube perfect numbers, I immediately see that I do have a 64 right there. So I'm not actually going to make a list of all of the factors for this one because it is a perfect number. 64 is 4 to the third power. So that means I have a triplet of 4's here. That's the same thing as 4 times 4 times 4, triplet of 4's. And so this triplet, because I have a cube root, they're all going to come outside together as just a 4. There's nothing left inside. So that is my final answer. Okay, last one, the cube root of 16. So let's make a list. For 16, we have 1 times 16 and 2 times 8. I'm going to stop right there because 8 is one of my perfect numbers. I'm rewriting this as the cube root of 8 times 2. The cube root of 8 is that 2. And then this 2 doesn't have a triplet, so it's going to stay inside. Okay, so the process is still the same. We're still using our perfect numbers. We're still making a list of all of the possible numbers that I can multiply together, looking for a perfect number. So let's go ahead and do some operations now. We'll do the first one as a review of square roots, and then we'll do the same thing with cube roots. The process is going to be pretty much the same as what we did previously. Okay, so for addition, recall that the index and the radicand both have to be the same. So in number 11, both of these are square roots, so the index is the same, and the radicand is 3 in both of them. So for this one, this is going to act just like a coefficient with a variable. The coefficient in front of this cube or square root of 3 is 1. So I am adding together those coefficients. 1 plus 4 is 5. And then my radical, which is acting like my variable, is going to stay the same. So I get 5 square roots of 3 as my final answer there. I do not add the 3's together because it's acting like a variable. All right, in number 12, we have 2 radicals that we need to simplify. Notice that the radicand is not the same. We have 81 and 24. So I need to simplify each of these radicals first, and then if they match, I'll be able to do the subtraction piece. Because these are both cube roots, I'm going to make my list of numbers, but I'm going to be looking for a cube root this time. So 1 times 81, 2 doesn't go into 81, but 3 times 27 does, and 27 is a perfect number. So I'm going to write this as the cube root of 27 times 3. Okay, then I'm going to put a little tail there to make sure that it doesn't look like I'm in my radical, and I'm also going to do the cube root of 24. So I'm going to write out my list of possibilities. I have 1 times 24, 2 times 12, 3 times 8, and there is my perfect number. So I'm going to write this as 8 times 3, and then I'm going to take my cube roots. Remember, 3 to the third power is 27, so that means this 27, I'm going to bring it out as a 3, because 3 times 3 times 3 is my triplet, and this guy doesn't have a triplet, so he's going to stay inside. 2 to the third is equal to 8, so a 2 is going to come out, and I'm going to still have my cube root of this guy here, 3. All right, so looking at it now, I have matching radicals, the index and the radicand, which means the coefficients out front can be subtracted. So 3 minus 2 is 1, which means that my final answer is 1 cube root of 3. And I don't need to write this 1 here, so I'm going to erase that. And that's my final answer. Okay, let's do multiplication. For multiplication, you only have to have the same index. So they both have to be square roots, or they both have to be cube roots, or whatever kind of roots you're taking. In number 13, they're both square roots, so I can go ahead and put these together. So I'm going to multiply the coefficients. That's -7 times 1, so that is -7. And then inside of the radical, I have 6 times 2. Now, you can write this as a 12 and make your list of factors, or you can break the 6 up, whichever you would prefer. So if I break the 6 up, just to do another way so you see lots of options, 6 is the same thing as 3 times 2, and then I have this 2 that's going to come down. And then I am taking a square root, which means I'm looking for a set of 2, a pair, and I have a pair. So I'm going to bring that pair outside and do -7 times that pair. That comes out as a 2, and inside my square root I still have that 3 left over. So then my final answer is -14 square roots of 3. If I had done this one the other way, I would have seen that I have 3 times 4, which would mean that I would have -7 times the square root of 4 times 3. The square root of 4 is 2, so it still gets me to that -7 times 2 square roots of 3 and gets me to my same answer down here. Okay, so last thing to review is division. These have to have the same index as well, just like they did previously. So in this one, I have a cube root on top and bottom. So I see an easy out for this one. I have a cube root of 2 numbers that are divisible, 20 divided by 5. So I'm going to put these together. And then 20 divided by 5 is 4. So it leaves me with the cube root of 4. And 4 is just 2 times 2. It's not a triplet of anything. So that means I am done with that one. I don't have further simplifying to do. All right, the last thing that we need to do is division when it's not super easy like this one, where 20 was divisible by 5. It gave us a nice answer, and we were all set. So let's rationalize the denominator with square roots to review how to do that. In number 15, I have the square root of 5 divided by the square root of 2. So I need to get that radical out of the bottom, but I can't just put them together because 5 is not divisible by 2. So remember what we did was we multiplied on top and bottom by a square root. That would get rid of the radical in the bottom. So if I multiply by a second 2, I will, in my denominator, have the square root of 2 times 2, or 4. And that's a perfect number that I can take the square root of. So I am going to do that in the top 2. 5 times 2 is 10. So the square root of 4 is 2. And the square root of 10, I can't simplify at all, so I'm going to write as a 10. And that one is all done because I got the radical out of the denominator. I rationalized it. Okay, so in number 16, I have the square root of 3 in my denominator, which I need to get rid of. So I'm looking for a pair of 3's down in the bottom. So I'm going to multiply by the square root of 3 over the square root of 3. Square root of 3 times square root of 3 is square root of 9, which is a perfect square. So that is going to turn into just a 3 in my next step. Up in the top, I have 2 radicals. They have the same index, so I can multiply them together. The coefficients are 9 times 1, so that's just 9. And I have the square root of 2 times square root of 3, which is the square root of 6. Now, I need to bring that over next. So 9 square roots of 3, or sorry, 6. I'm not, however, done with this yet because I have a 9 outside of the radical and a 3 outside of a radical. And 9 divided by 3 simplifies. It is 3. So my final answer is 3 square roots of 6. Okay, so let's extend this idea to cube roots now. If I have a cube root, then I am looking for a triplet. I'm not just looking for a pair. So I'm going to multiply by a radical. That's a cube root again. But I'm not just going to put a 3 here because that would only give me the cube root of 9, and 9 is not a perfect cube. My perfect cube with 3's is 3 to the third is 27. I'm trying to get a 27 in my denominator. So I want to multiply 3 times something to get 27, and 3 times 9 is 27. So that means I'm going to multiply by the cube root of 9 on top and on bottom. On my top, this 15 is outside of the radical, so they're just going to be multiplying without actually like combining, so we're just going to let them hang out. I can take the cube root of 27 though, because it is 3. And then my top is going to come along with me. I am not, however, done yet because my numbers outside of the radical, 15 and 3, those are divisible. 15 divided by 3 is 5. And then I've got my radical that's just going to be stuck there with me. So now I'm done. Okay, so I also want to point out that another way to think about this at this step is that when you have your cube root of 3, because you're looking for a cube, we can multiply. We have 1 3 here. We need 2 more 3s to have a triplet, which is what a cube root is asking us for. So I can also think about this as multiplying by 2 more 3s, because that would give me down in my denominator 3 times 3 times 3. And that is a triplet that comes outside of the radical and leaves me just with the 3. Either way is a perfectly fine way to think about that problem, and you're going to get the same thing. So let's look at one last one that is a little bit harder this time. So I have in my denominator the cube root of 4. Now you can think about 4 to the third is 64 and do it that way. But you can also notice that 4 is 2 times 2. So if I change that to a 2 times 2, now what I'm looking at multiplying is I want to multiply by a cube root that gets me a triplet. And this means I already have a pair. I have 2 2's. So I only need 1 more 2, and that in my denominator is going to give me a triplet of 2's. What this will do, because I made my radicand of 4 into a smaller base, it will mean that I won't have extra simplifying to do at the end. So let's watch how this works out next. My numerator is going to be 2 times the cube root of 2, and then my denominator, this triplet of 2's, because I'm looking for a triplet, comes outside of the radical, and then I'm done. Because 2 isn't divisible by 3, so I can't go any further. If I had done this as a 4, so if I'd done 2 cube roots of 4, and I would need to get up to 64, so I'd have to multiply by 16, 4 times 4, to get a triplet. If I did the cube root of 16, that would give me the cube root of 64 in my bottom, and 2 cube roots of 16 in my top. So the cube root of 64 would simplify to 4. And then I would still have more work to do, because I could simplify 2 over 4 to 1/2, but I could also simplify this cube root of 16, because 16 is 2 times 2 times 2 times 2. So you need to be really careful here, because this looks done maybe, but it's not done. This numerator simplifies more. And if you don't want to have to deal with simplifying another radical again through these next steps, then you will need to use the smallest base like I did up here. So this method is what I'm recommending, not this method. It's easy to make mistakes using that method. Okay, so that wraps up what I wanted you to try today. So I'd like for you to go ahead and try the Now You Try problems. You are going to be converting between radical and rational exponents. You should be comfortable with the exponent rules, which we did previously, and this was just a review of. And then you're doing some new operations, or the same operations, but with cube roots instead, so it's a little new. And then rationalizing the denominator, a little bit of square roots, but also some cube roots now, since that is new. Go ahead and give those a try.